Hello everyone, my today's topic is studying the shape of data using topology. Now over here, data I refer to geometrical shapes. Now the story of data explosion is by now a familiar one, and it is used throughout science, commerce, engineering and government. So now at present, our data often encodes extremely valuable information, but is typically large, noisy, and complex, so that extracting useful information from the data can be a real challenge. So now there is something called as it is a developing branch of statistic, TDA. TDA stands for Topological Data Analysis. Now this is a developing branch of statistics. Now this TDA, what happens over here is our data, when it encodes extremely valuable information and it is typically large, so it is containing a valuable information. It is large, noisy, as well as complex. So to overcome all this, TDA is used to seek to address aspects of this challenge. So now in last 15 years, there has been a surge of interest and activity in TDA, yielding not only practical new tools for studying data, but also some pleasant mathematical surprises. There have been applications of TDA to several areas. So now few of them are science and engineering, including oncology, astronomy, neuroscience, image processing, and biophysics. Now science and engineering though we know already. Oncology, it is a study of human body. Then astronomy though we know. Neuroscience, it is a study of nerves. Image processing the image in different ways, like editing the images and all. Biophysics is a branch of physics. So now the basic goal of TDA is to apply topology, one of the major branches of mathematics, to develop tools for studying geometric features of the data. Now in this we'll be studying about geometric features of data. Explain what topology is, and discuss how we use topology to study the geometric features of data. And at the end, we'll describe an application of TDA to oncology, where Their insight into the geometric features of data offered by TDA led researchers to discover a new subtype of breast cancer. So now, in this data, when I say data, I simply mean finite set of points. In space. In general, the space which is in our points can have many dimensions. But for now, we are just considering either 3D or 2D dimensions. For a concrete example, each point in a data set in 3D space might correspond to a tumor in a cancer study. And the XYZ coordinates of the point might each correspond to the level of expression of a different gene in a tissue sample of the tumor. So now what do I mean by geometrical features of data? Now let us just take an example of the clusters that I have drawn over here. This is a data set with 3 clusters. Now this I have represented in 2D space. As first example, let us see when we see that the data breaks up into 3 distinct clusters. Clusters like these are first type of geometric features of data that we study in TDA. We'd like to count the number of distinct clusters in the data and partition the data into its clusters. We'd like to be able to do this even when the cluster structure of the data is corrupted by noise. I have not represented the noise cluster over here till now. So now let us see what is a noise cluster. The problem of detecting clusters in data is in fact an old and well-studied problem in statistics and computer science, but TDA has recently introduced some new ideas and tools to the problems. So now you can clearly see the noise cluster as well as the other 3 data set of clusters. There is a difference. You can see that noise cluster, all the points are combined very near to each other. Whereas when we come to the data set, then you can see that there is a difference between the points. So now this difference, to overcome this problem, a second kind of geometric feature of data we study in topology data analysis is a loop. So now this is an example of a loop in a data set. Again, we'd like to able to detect a loop in a data set even when it is corrupted. So now this figure 4 shows data set with loop. So now if we see the 5th figure, that is a data set with noise loop. So now this is a noisy loop. A third kind of geometric figure we study is in TDA is a tendril. So now this figure 6 will show you how the representation of a tendril is. Figure 5 depicts data set with 3 tendrils emanating from a central core. Now, in a data set with this sort of structure, we'd like to detect the presence of the tendrils, count the tendrils and partition the data into different tendrils. So now this is a tendril. So I can divide this tendril. At the same time, I can count the number of tendrils and I can partition the data into different tendrils. So I can divide this into different parts. Also, you can see that in a tendril you can form a loop. I can just form a loop over here. So the objective of research in TDA is to develop tools to detect and visualize these kinds of geometric features, and to develop methodology for quantifying the statistical significance of such features in randomly sampled data. Because much of the data arising in scientific application lives in high dimensional spaces. The focus is on developing tools suitable for studying geometric features in high dimensional data. Dimensional data. So now, why we should be interested in such studying such features of data in first place? The key premise behind this line of research is that insight into the shape of scientifically relevant data has a good chance of giving insight to the science itself. Experience has shown that this premise is a reasonable one. Cluster analysis is used as a matter of course throughout the experimental science to extract scientific information from data. The study of loops and their higher dimensional analogues has recently offered insight into questions in biophysics and natural science statistics. And as well as I will describe in the last session of this article, the study of tendrils has recently offered insight into oncology. As noted above, TDA studies the geometrical features of data using topology. So now TDA studies the geometric figures of data using topology, and topology is the study of properties of a geometric object that are preserved when we bend, twist, stretch, and otherwise deform the object without tearing it. The primary example of such a property is the presence of holes in the object. As such, topology is concerned largely with the formal study of holes. Topology is concerned with formal study of holes. So now, to anyone who has ever eaten a slice of Swiss cheese or a donut, the notation of a hole is a geometric object is very much familiar and intuitive. The idea that the number of holes in a geometric object doesn't change when we bend, twist and stretch the object is similar intuitive. Just take an example of a donut. Now when you have a donut, unless and until you break the donut, obviously you can't make this hole a different one. When you twist it, or unless and until it is dead, either you twist it, either you bend it, the hole will remain as it is. In topology, we distinguish between several different kinds of holes. A hole is the center of a donut, is an example of a first kind of hole. The hole space in an inflated tight balloon is an example of a second kind of hole. That is, a balloon will have the hole inside, which is called as a space. It will contain air inside, which is considered as hole. Now, in geometric objects in more than 3 dimensions, we may also encounter other kinds of holes that cannot appear in object in our 3D world. As intuitive as the motion of a hole is, there is quite a lot to say about holes, mathematically speaking. In the last century, topologists have put great effort into the study of holes and have developed a rich theory with fundamental connections to most other areas of modern mathematics. One feature of this theory is a well-developed set of formal tools for computing the number of holes of different kinds in a geometric object. Now, TDA, it aims to put this set of tools to use in study of data. Computations in the number of holes in a geometric object can be done automatically on a computer even when the object lives in a high dimensional space and cannot be visualized directly. How do we use topology to study the geometric features of data? So now, topology, without pretending to give a full answer to this question, I'll mention some of the basic ideas. To begin, I'll describe a primitive strategy for studying data using topology that, while unsatisfactory for most application, is the starting point for what is done in practice. As mentioned above, topology offers tools for computing number of holes and components in a geometric object. We would like to apply these tools to our study of data. However, a data set X of n points in space has n components. And number of holes at all. So directly computing the number of holes and components of X will not tell us anything interesting about the geometric features of the X. To study X using topology, then we will consider not the topological properties of X directly, but rather the topological properties of a thickening of X. Assume that X is a finite set of points. In 2D space. I'll consider delta a positive number. Now I'll consider the set of all points in a plane within distance delta from a small point in X as T of X comma delta, and this is the thickening of data set X. Data set. For example, let X1 be the data set of let X1 be the data set. So now I've taken X1 as a data set of figure 1. Now figure 6, this shows the T of X1 comma delta 1. Now the red one represents the delta 1 and the black goes for the X1. The original data is represented in black color. For second example, I'll be taking X2 as my data set and T of X2 comma del 2 will be some delta 2 for the positive number and this will be represented again in red, and X2 the original data and it will be again represented in black. So now, for especially nice data sets X and good choices of delta, the clusters in X will correspond to components of T of X comma delta, and the loops in X will correspond to holes in T of X comma delta. For instance, we have seen in the previous figure that the cluster x1 corresponds to the components of T of x1 comma delta, and in this figure the cluster x2 corresponds to T of x2 comma delta, or this is a loop. Instead of saying it is a cluster, I will be saying it is a loop because it is joined and connected. Thus, for nice data sets X, we can insight into geometric features of X by studying the topological properties of T of X comma delta. Now, the same strategy also works for studying the geometric features of data set sitting in a high dimensional space, in which case the data cannot be visualized directly. Most data we encounter in practice are noticed as those shown in figure 1.3, and though the primitive TDA strategy we have described does extend in data in high dimensional spaces. For typical data sets X in any dimension, the strategy has several critical shortcomings. For one, topological properties of T of X comma delta can depend in a very sensitive way on the choice of delta, and a priori it is not clear what the correct choice of delta should be, or if a correct choice of delta exists at all in all sense. Also, the topological properties of our T of X comma delta are not all the robust to noise in X, so that this strategy will not work for studying the geometric features of noisy data sets such as those in figure 2 and 4. Moreover, this approach to TDA is not good at distinguishing small geometric features in the data from large ones. Thus, dealing with most data, one encounters in practice more sophisticated variants of this basic strategy are required. One central idea in this direction is that it is much better to consider at once the topological properties of entire family of the objects of T of delta x comma delta. As delta varies, then it is to consider the topological properties of T of x comma delta for a single choice of delta. The idea behind persistence homology, a key technology tool, is TDA. Now, the problem of studying tendril in data is closely related to the problem of studying clusters too. To see this, let us consider the following figures. So now this is a tendril which we have already seen in figure 6. So now in this tendril I had already said that there exists a central core. Now I have represented the central core in green color. If we were to have a principled way of identifying the central core of data, then by removing the central core we obtain a data set with 3 distinct clusters. So these are the 3 distinct clusters what we get, where each cluster corresponds to a tendril in the original data set. It is natural to expect then that some of the topological tools that are useful for studying clusters can be extended to the study of tendrils, and in fact this is the case. Now at the starting of the session I had said that I'll be speaking about a new subtype of breast cancer. The author studied a data set describing the gene expression profiles of 295 breast cancer tumors. Now each from a unique patient. The dataset consists of 295 points sitting in 24,479 dimensional space. Each point corresponds to one tumor, and roughly speaking, each of 24,479 coordinates of the point specifies the level of expression of one gene in a tissue sample of the corresponding tumor. To begin their analysis of the data, the researchers mapped the data from 24,479 dimensional space into a 262 dimensional space. In a way that preserves aspects of the geometric structure of the data relevant to the cancer, while eliminating aspects of the structure not relevant to the cancer. The researchers then studied the geometric features of the data in 262 dimensional space using a DDA tool called Mapper. They discovered a 3-tendril structure in the data loosely analogous to that in the data figure 5. In addition, they found that one of these tendrils decomposes further, in a sense, into 3 clusters. And we have already seen that in figure 10. One of these clusters, they observed, corresponds to a distinct subtype of breast cancer tumor that had hitherto not been identified. This subtype, which authors named CMYB+, comprises 7.5% of the data set, or 22 tumors. Tumors belonging to CMYB+ subtype are genetically quite different than normal tissue, yet patients whose tumors belong to this subtype had excellent outcomes. Their cancers never metastasized and their survival rate was 100%. A standard approach to the classification of breast cancers based on clustering divides breast cancer into 5 groups. The CMYB+ subtype does not fit neatly into this classification scheme. So these tumors divide among 3 of the groups, the results of Nicolau, Carlson and Levine. Thus suggests a nuance to the taxonomy of breast cancer, not accounted for in the standard classification model. So these results illustrate how the tools of TDA can be useful in helping researchers tease out some of the scientific information encoded in their high-dimensional data. They are just one of a growing number of examples where TDA has facilitated the discovery of interesting scientific information from data. Still, in spite of good progress in the field over the last several years, there's still much to be done in terms of fleshing out the mathematical and statistical foundations of TDA, and in terms of algorithm and software development also. So that's it about the study of data using topology, or the shape of data using topology. Thank you for watching the video.